Hello. So, in the previous lecture we looked at the laminar fully developed flow in a cylindrical channel which has circular cross section, and we obtained the equation for the velocity profile in such a arrangement by simplifying the mass and momentum conservation equations in the cylindrical coordinates. Today in this lecture we will look at another problem, which is flow between two concentric cylinders. Now, when we look at concentric cylinders, that means these cylinders, the two cylinders are they have same axis, and if you look at from the top you will see the cross section as two concentric circles. The liquid is filled between the two cylinders, as you can see by the blue color here. Now, you can have different arrangements. For example, you may have if the arrangement is vertical, you may have the flow because of gravity driven in this cylindrical cavity or in the annular gap between the two cylinders. So, that is also you can consider that a case of a falling liquid film between falling liquid film on a cylinder. It might be the inside the cylinder or outside the cylinder, and you will need to treat the outer boundary as the free surface or inner boundary as the free surface, depending on where the film is. But what we are going to look at in this lecture is that the flow is driven by the motion of one of the cylinders. So, in this case the outer cylinder rotates with an angular velocity of omega, and because of the shearing motion, because of the shear caused by this cylinder, the fluid starts rotating. So, it is a shear driven flow. If you remember, when we talked about flow between two parallel plates and the upper plate moving with a velocity u. So, again the flow was driven by shear in that case. Okay. So, the gravity is acting in the negative x direction. You can see the arrangement, the coordinate arrangement, that r and theta coordinates here, and the axial coordinate is taken as x coordinate. The radius of the inner cylinder is r1 and the radius of the outer cylinder is r2, and we need to simplify the mass and momentum conservation equations, find the velocity profile. So, in this case the velocity profile, because the outer cylinder is moving, so there will be a velocity in the angular direction here, and there will be no motion along the vertical direction, because there is nothing to drive the flow along that direction, or we can neglect the motion along the vertical direction. Okay. So, this is actually gravity acts in the negative x direction. So, we can neglect the motion in the vertical direction, and there will be, as we will see, there will be no radial component of velocity. Okay. So, we can start by writing down the mass and momentum conservation equations in the cylindrical coordinate system, and then let us write down the assumptions. So, the first assumption, that we will assume that the flow is steady. Of course, we will also assume that the flow is laminar. So, all such cases which we are solving the finding the analytical solution for, they are in all such cases the flow is laminar. The flow is steady, then the flow is incompressible, and the flow is axisymmetric. So, which means that there is no variation of properties in the theta direction. Remember, when we talked about flow in a circular channel, then we looked at the theta component of velocity, or v theta was also 0, but here v theta will be non-zero, and the axisymmetric flow simply means that the flow is symmetric about the axis. So, v theta will be same at every theta. So, that means del v theta over del theta will be 0, and the gradients of other velocity components along the theta direction, which is del over dou over dou theta, will be 0. And there are no velocity component and velocity variations in the x direction. Okay. So, if we write down these assumptions in terms of equations, the first assumption of steady flow will simply mean that dou by dou t for all the variables, all the velocity components, and rho they are 0. Okay. The compressible flow will mean that in the continuity equation dou rho by dou t will be 0, and rho is a constant. So, your continuity equation will come in this form, which is in vector form del dot vector v. The axisymmetric flow will mean here that dou by dou theta for all the velocity component as well as pressure will be 0, because it is not pressure driven flow, though the flow is happening along the theta direction, but this is because of the shearing motion. And we will neglect the velocity component in the x direction, even if there would have been any flow along the x direction. So, we will neglect that, and there are no gradients along the x direction. So, del over del x of v r of v theta and u, which is the axial velocity component, they are 0. Okay. Now, let us start with simplifying continuity equation. So, when we look at the continuity equation, these two terms will be 0. This term will be 0 because the flow is axisymmetric, and del over del theta of v theta will be 0. This is 0 because u is 0, or you can also say that dou over dou x of u is 0. So, that will simply mean that dou over dou r of r v r is equal to 0, which when integrated will give us that v r is equal to c by r. We can also take into account the fact here that the derivative of v r with respect to theta is 0, because the gradients along the theta direction is 0 or are 0, and dou over dou x of v r is 0 because gradients along the x direction are 0. So, that means v r is not a function of theta and x, and we can use this as an ordinary derivative also. So, r v r will be a constant. Now, r v r is a constant. So, v r will be constant divided by r. Now, we can use the boundary condition at the surface of the inner cylinder, which is stationary. So, because of the no slip boundary condition, there v r is equal to 0. So, that means if v r is equal to 0 at the inner cylinder, then v r needs to be 0 everywhere in the liquid, in the entire annular space. So, that means v r is equal to 0. We had that v axial component of velocity, which is u, is equal to 0, and v r is equal to 0. So, we are left with only one component of velocity, which is non-zero, and in this case this is v theta. So, now we will try to simplify the equations of momentum conservation or Navier-Stokes equations in the cylindrical coordinates. So, first we look at the momentum conservation equation in r direction, and the first term will be 0 because the flow is steady. The second term will be 0 because v r is equal to 0. The next term will be 0 because we have dou over dou theta as 0 for all the variables, and then next term, this term is 0 because dou by dou x of V r is 0. There is no component of gravity, gravity acts in the negative x direction. So, there is no component of gravity along the radial direction. So, this term is 0 and this term is 0 because V r is equal to 0. Next term is 0 because dou over dou theta and second derivatives will be 0. This term will also be 0 because dou over dou theta is 0 and the last term will be 0 because V r is equal to 0 or dou 2 by dou x 2 will be 0. So, what we have from this is the two terms which are left, which we are left with. So, that says dou p by dou r is equal to rho v theta squared by r. So, there will be a pressure gradient because v theta will be non-zero. So, we will have a pressure gradient along the radial direction, which is if you look at it, it resembles the centrifugal force. Okay. Now, let us look at the momentum conservation equation along the theta direction. The first term will be 0 because the flow is steady. The next term will be 0 because V r is equal to 0. Then dou by dou theta is equal to 0, V r is equal to 0. So, this term will be 0 and dou by dou x is equal to 0 for all the velocity components. So, this term will be 0, no component of gravity along the theta direction. Then the derivative along the theta direction and second derivatives are 0. So, dou 2 by dou theta is 0. So, this and this term they will be 0 and the last term is 0 because there are no derivatives along the x direction or dou 2 by dou x 2 is 0. So, now from this we will be left with the viscous term and there is no pressure variation along the theta direction. So, dou p by dou theta will also be 0. So, we will left with only viscous term which is equal to 0 and from this we will be able to find the velocity. Now, the last momentum conservation equation which is along the x direction. So, the first term is 0 because flow is steady, the next term is 0 because V r is equal to 0 and the third term here is 0 because u is 0. Actually, in this equation most of the terms will be 0 because u is equal to 0. So, we can say all of these terms will be 0 and there is a that rho g x minus dou p by dou x. So, you will have a hydrostatic pressure gradient along the vertical direction. Now, we will take this term and integrate it so that we can find the velocity profile. So, we can integrate this term and we know that V theta is not a function of theta because dou v by dou theta is equal to 0 and we also know that dou v theta by dou x is equal to 0. So, v theta is only a function of r. So, we can as well use ordinary derivative in place of partial derivative. So, when you integrate it you will get 1 over r dou by dou r of r v theta that is equal to C 1. Now, when you integrate or when you simplify it, you will get dou by dou r of r v theta is equal to C 1 r. You can integrate it further. So, you will get r v theta is equal to C 1 r squared by 2 plus another constant of integration which is C 2 and then you can find v theta. So, that will be C 1 r by 2 plus C 2 by r. So, that is the velocity profile in the annular space between the two cylinders and you can see that this is a function of r. There are two constants C 1 and C 2 which we need to find. So, we need two boundary conditions here, and we have two walls. On the inner wall, at r is equal to r 1, v theta is equal to 0, because the cylinder is stationary. The outer wall, where r is equal to capital R 2, v theta is equal to omega r 2. So, we can use both the boundary conditions here. So, when we use the first boundary condition, that at the inner cylinder r is equal to capital R 1, v theta is equal to 0. So, we will get 0 is equal to C 1 R 1 by 2 plus C 2 by R 1, and the second boundary condition will give us that at r is equal to capital R 2, v theta is equal to omega R 2, that will be equal to C 1 R 2 by 2 plus C 2 by R 2. Now, we can simplify these equations and can find the values of C 1 and C 2. So, you can multiply the first equation by R 1 and second equation by R 2, and you can eliminate C 2. Then, once you eliminate C 2, from that you will get C 1. You can subtract the equation, the second equation from the first equation, and you will get the value of C 1. Once you get C 1, from this you can say C that C 2 is equal to minus C 1 into r squared by 2. So, C 2 will be C 1 into r squared by 2. So, 2 omega into minus 1 minus r squared by 2. Okay. So, so you can use you can find the equations equation after substituting the values of C 1 and C 2 in this equation. So, you get the velocity profile, which is v theta is equal to omega r 1 divided by 1 minus r 1 by r 2 whole squared into small r by capital R 1 minus capital R 1 by small r. So, this is a function of r. Now, the next task is to find the shear stress distribution. So, to find the shear stress distribution, because the flow is again along one direction only. So, you will have only one component, or say among the 6 shear stresses, you will have only 2 shear stresses, tau r theta or tau theta r, which is non-zero. So, that is the general expression for tau r theta in the cylindrical coordinates, and because dou by dou theta is 0 or V r is 0. So, this term will be 0, and you will have tau r theta is equal to mu into r d by d r V theta by r. You can use ordinary derivative, because V theta is a function of r only. Okay. So, you can use the expression for V theta to find the derivative. So, when you find derivative of V theta by r with respect to r, then you will need to multiply this equation by r. All this is constant. So, you will have this constant, say omega r 1 divided by 1 minus r 1 by r 2 squared into the first term in bracket will become a constant, because you divide by r. So, it will become 1 over r 1. So, that will be 0, minus the second term will be r 1 divided by small r squared. So, you will have to differentiate r raised to the power minus 2. When you do that, so you will get minus 2 into r raised to the power minus 3, or you can write divided by r cubed. So, the derivative will be of V theta by r will be this expression. Now, you have to multiply this with small r. So, one of the r will be cancelled here, and you will get tau r theta is equal to mu times 2, which comes from here, 2 into omega divided by 1 minus r 1 by r 2 squared into r 1 squared by r. So, we had a r 1 here. So, this should have been r 1 squared. So, you will have r 1 squared divided by small r squared, because one of the r will get cancelled when you multiply by this r. So, that is the expression for tau r theta, or the shear stress in between the two cylinders as a function of r. Now, we will just look at the expression here, which is for the velocity, and try to simplify it with some assumptions. So, if we say that small r is equal to capital R 1 plus y. So, let us say you have the two concentric cylinders, and you assume that the distance from the inner cylinder is y, and the distance between the two cylinders is delta. So, you can write r is equal to, small r is equal to capital R 1 plus y, and R 2 is equal to R 1 plus delta. Okay. So, delta is a constant here. Now, we can substitute these, or you can also have delta is equal to R 2 minus R 1. So, when you substitute this in the expression for velocity, you will get v theta is equal to omega R 1 as it is. Now, we can simplify this. So, we can write this R 2 squared minus R 1 squared. Okay. The terms in the bracket, we will replace small r by R 1 plus y here. So, this will become R 1 plus y divided by capital R 1 minus R 1 divided by R 1 plus y. Now, we can write this R 2 plus R 1 into R 2 minus R 1. So, that is what we have done here. Then we can simplify the term in the bracket. So, when you take LCM, it will be R 1 into R 1 plus y. The first term become R 1 plus y squared minus R 1 squared. Okay. So, you can simplify the term in the bracket again. So, this will remain R 1 into R 1 plus y. When you write this, it will be R 1 plus y minus R 1, which will be y only, and you will have R 1 plus y plus R 1. So, that will be 2 R 1 plus y. Now, you can also replace that R 2 minus R 1 is equal to delta here. So, we have replaced this R 2 minus R 1 with delta, and now if we assume that the distance between the cylinders, or the space between the cylinders is very thin, or the film between the cylinders is very thin, the gap between the cylinders, which is delta, is very small when you compared with R 1. So, in that case, what will happen, that you can also assume that R 2 and R 1, they are approximately equal. So, you can write them equal to R. Now, if we substitute this approximation in here, so what you will get, you can write R 1 plus R 2 in the denominator here as 2 R. This R 1 and this R 1 will get cancelled. You will have omega, and R 2 squared you can write as R squared, because y is small when you compare with R 1. So, you can neglect this y, and this expression will be 2 R 1 or 2 R. So, 2 R multiplied by y divided by R 1 plus y, you can write as R 1 or R here. So, you can write this as, now R and R will cancel out. So, what you will be left with, 2 will cancel out, and what you will be left with as y over delta into omega r. So, y over delta is, so if you look at this, the flow between two parallel plates, and the upper plate moving with a velocity omega r. So, the linear velocity profile, you will have y over delta omega r. So, in the limit, when the gap between the cylinders is very small as when compared with the radius of the cylinder, then you can very well assume the flow to be flow between or as the flow between two parallel plates. So, you can think of that means what does this suggest, approximation suggests that you have a very big cylinder and at the top of cylinder or in between the cylinders the effect of curvature will be very small and you will have this expression to be valid. Okay. So, in the viscometer when one have the viscometer arrangement, generally what happens that there is a cylinder, outer cylinder, and in this outer cylinder the liquid is filled and the inner cylinder is introduced and it is hanging by a wire here. Now, one can rotate this cylinder using a motor arrangement or one if one can rotate at a specific angular velocity. So, you can have a omega r fixed and because of that there is flow between the two cylinders. Okay. So, this arrangement is slightly different from the problem we just discussed in that the inner cylinder moves here and the outer cylinder is fixed, but that is just a small change in the boundary conditions and we can obtain the expression for this case where the outer cylinder is fixed and inner cylinder is moving. Okay. So, such arrangement is quite often used as a viscometer and you remember that this arrangement where the flow was shear driven between two parallel plates, we used to call it as Couette flow. So, this arrangement is called when there are two infinitely parallel or two parallel infinitely long and infinitely wide plates, we call it planar Couette flow, whereas when it is the flow between two infinitely long cylinders and one of the cylinders is moving or they may be moving with a they might be moving both of them might be rotating and their angular velocity are different. You can find such a general case also but then the boundary conditions will be that at the inner cylinder you will have at small r is equal to capital R1 V is theta is equal to omega R1 and at the omega 1 R1 and at the outer cylinder you will have V theta is equal to omega 2 R2. So, you will find you will be able to find a general expression. The flow, this such kind of flow is generally known as circular Couette flow. Okay. So, if we summarize what we have discussed today, we discussed a coannular arrangement of circular cylinders where the cylinders are coaxial and found the velocity profile when the outer cylinder is rotating and we used simplified the mass and momentum conservation equations, used the boundary conditions for such case and we noted here in this case that even though the flow is axisymmetric, but V theta is non-zero. So, dou p by dou theta was 0 and all the three velocity components their derivative along the theta direction will be 0. That is what the axisymmetric flow mean. And in this case there was no pressure gradient to drive the flow was driven by the shear. The pressure vary along the radial direction. So, we obtained this relationship and we can substitute the value of V theta here and also calculate what is the pressure gradient along the radial direction. Okay. And we have also seen that in the limit when the distance or when the separation distance between the two cylinders is very small as compared to the radius of the cylinder, then we obtain the equation for a planar coed flow. The velocity profile is same that in case of a planar coed flow. Now, when the cylinders are moved with a very high rotational speed, then what happens that above a certain speed, let us say if the inner cylinder is being rotated with a speed. So, above certain speed there are vortices forming, the flow becomes unstable and there are vortices forming and these vortices are known as Taylor vortices after Taylor, after whom this cylindrical arrangement is also named as Taylor coed flow. So, he looked at the instability in such cylindrical arrangement. Okay. So, we will stop here. Thank you.